Alright, so in the past two videos, we introduced the Laplace transform, we proved it was linear, and we found what the Laplace transform of a function multiplied by an exponential is, e to the at. It's just a Laplace transform of the original function, evaluated at s minus a, shifting by a. So, now that we know all of this, let's delete, run out of space, and let's scroll back up to the top and think about what might be the Laplace transform of our trigonometry functions. So, the Laplace transform of the sine of some constant a times t, and what might the Laplace transform of the cosine of some constant a times t be? What might it be? Alright, so this is the first place where I'll not caution you. Where I'll caution you not to go immediately to the integral definition. Because if you immediately go to the integral definition for the Laplace transform of the sine of at, what you'll be met with is the integral from 0 to infinity of the sine of a times t times e to the negative st dt. This is the definition after all. And this is a gruesome form, because in order to find what this integral is, we would need to do something akin to double integration by parts. On the very first integration by parts, we would pick sine of at to be our u, so we differentiate sine of at, we would get a times the cosine of at, and then this is blah in an integral, plus blah, and then on the very next integration by parts, we would choose the cosine of at as our u. So what we would get in our integral is blah plus, and then blah plus, and now the integral from, and then the derivative of cosine is negative sine of at, and then we get blah dt. Okay? So this is what double integration by parts would roughly look like. Lots of blahs, and then an integral of negative sine of at. And this integral here would be the exact same, because we'd still have the e to the negative st. So we have the e to the negative st, and it'd be bounded from 0 to infinity. Okay. And what we'd be left with is this integral, which is itself the Laplace transform of sine of t, in an equation with the Laplace transform of the sine of t. So if we named the Laplace transform of the sine of t for our own health, x, then what we would get is that x equals a lot of blah plus big bracketed expression with a lot of blah plus x. And then we could algebraically solve this for x. And that is the gross way to do it, because I have a much cleaner way to do it. And alright, so let's scroll down a bit. That's the method that's usually shown, but I believe I've even made a video on this before because I thought it was so cool when I learned it. I'm going to show you how to find the Laplace transform of the trigonometry functions with complex exponentials. Alright, buckle your seatbelt. Prepare to be amazed. We can write the sine of at as our first step as a certain sum of complex exponentials. And in order to know what's going on here, you got to remember Euler's formula, which says e to the I times something equals the cosine of that something plus I times the sine of that something. This is where we get e to the I pi equals 1. Alright. Or, sorry, negative 1. Excuse me. E to the I pi equals negative 1 because cosine of pi is negative 1 and I sine of pi is 0, so this goes away. Alright, that aside, this is Euler's formula. Super awesome. With it, we might have the observation, hey, cosine's an even function, sine's an odd function. That's just a way of saying that the cosine of negative something is the same as the cosine of that something, whereas the sine of negative something is negative sine of that something. So sine is odd, cosine is even and odd functions. We might notice, interesting. If we took the cosine of negative x, so first of all, just the cosine of x plus the I sine of x, I don't know why I did parentheses there and not on the cosine. If we took the cosine of x plus I sine of x, let's say we were trying to get at the cosine of x. If we used negative x's, we could say cosine of negative x plus I times the sine of negative x. Our observation now, okay, we just go forward. Cosine's even, sine's odd, so we know this is just going to be the same as the cosine of regular x, and I'm actually just going to, well, okay, I'll write it. Cosine of negative x is just the cosine of positive x minus I sine of x. Alright, so we're paying attention to these two. Now, cosine of x plus I sine of x. Cosine of x minus I sine of x. If we're looking for cosine, we could just add these two. So say add, and the signs are going to go away, and we're going to get 2 cosine x. We could say add and divide by 2. So I'm saying we could say e to the ix minus e to the negative ix, actually plus, divided by 2. This equals the cosine of x. Similarly, if we subtracted them, the signs would get multiplied by 2, and we would have the cosines going away, and we could divide by 2i. So e to the ix plus e to the negative ix divided by 2i, to get rid of this I term also, this equals the sine of x. Amazing, right? Now, using this same complex exponentials trick, we can say that the sine of a times t is going to be e to the I a t, and because we're doing sines, we're going to add plus e to the negative I a t divided by 2i. And this is going to make taking the Laplace transform of sine of at much easier. Alright, now, in order to actually make space, I'm going to erase this all, but keep it in your mind, and you can always pause and rewind back to that part in the video if you want to understand it more. Alright, this is sine of at, and this tells us that the Laplace transform of the sine of at, Laplace transform of the sine of at, is really just the Laplace transform of this, e to the I a t, plus e to the negative I a t, divided by 2i. Alright, now this is going to be easier to solve because we know two things. The Laplace transform is linear, so we can pull out the 2i. It's going to equal 1 divided by 2i, because 2i is a constant, it's complex, that doesn't matter. Now, this is just the Laplace transform of, and because it's linear, also, we know we can break apart the Laplace transform by the plus. It's going to be the Laplace transform of e to the I a t plus the Laplace transform of e to the negative I a t. And that's that. We know the Laplace transform, if you recall, we know the Laplace transform of e to the something times t is equal to, again, a shifted Laplace transform. So it's the Laplace transform of 1, because we're multiplying 1 in here sneakily. So Laplace transform of 1 evaluated at s minus a, which is 1 divided by s minus a. Well, if this is the Laplace transform of e to the at, we can surely just use it. So 1 divided by 2i, it'll extend to the complex case too. Laplace transform of iat, in this case, our a is ia. So we say 1 divided by s minus ia. And then plus the Laplace transform of e to the negative iat. So in this case, our a is negative ia. So divided by 1 over s plus ia. Now if we do a little bit of simplification, what we're going to get is that this is 1 divided by 2i times, and then what we're going to do is we're going to multiply this fraction by s plus ia divided by s plus ia, which is the same as just doing nothing in the multiplication, because multiplying by 1. So we're going to get s plus ia divided by s minus ia times s plus ia with appropriate parentheses. And then on this one, again, this is making so the denominators are going to line up. We're going to multiply by s minus ia divided by s minus ia. So we're going to get s minus ia divided by s plus ia times s minus ia. Ugh, crowded on space. Alright, there we go, we made it. And now notice that these denominators are exactly the same, so with just switching the order of multiplication in this case. So we can rewrite this as the denominators combined, okay? So what we're going to get is that this is, notice also that the IAs are going to, oh, wait a minute, I think something went wrong. Wait a minute. You're probably just slapping your forehead, hand in the forehead. This plus here means cosine, if you remember our identity that we figured out. So if we want to be doing the sine, what we actually need to be doing is subtracting here. So if we subtracted here, then we would have subtracted here, and we would have subtracted here, we would have subtracted here, and would have subtracted here. That was a silly mistake to make. On the bright side, it's going to make solving for cosine easier, because we just divide by 2 instead of 2i in the cosine case, but in this case we are dividing by 2i. Okay, so I know you're probably palming your forehead at this point, but alright, good. Now we have the true Laplace transform of the sine of at. And what it's going to be is, notice now, we have s minus s over here, so the s's are going to cancel out. Cancel, cancel. And the ia minus negative ia is just plus ia. So we're going to get 2ia divided by, and now we have this multiplication. So s minus ia times s plus ia. Okay, another thing cancels out. This is looking good. 2 i's cancel out. Okay, now we're left with a divided by this multiplication. Now, if you remember, we could just multiply this out, but if you remember from algebra class, we have the difference of squares, s plus x, or really I can just say x plus n times x minus n is just x squared minus n squared, which just happens because you do xx as you FOIL, negative nn, and then you do negative xn and positive xn, and they cancel out anyway. And we notice here we have, and this isn't x to the n, it's x squared minus n squared. So we have s minus ia times s plus ia. We can do the same exact thing. So we're going to get s squared, so s squared minus ia squared, and then we're going to get this s times ia positive, and then s times ia negative there. So that's going to cancel out. We don't even have to worry about this. And finally, we can rewrite this for the last time as a divided by s squared negative ia squared. I squared is negative 1. So negative negative 1 is positive 1. So plus a squared. And this is the nicer way to get to the Laplace transform of the sine of at. The Laplace transform of the sine of at is that a divided by s squared plus a squared. And if you want to do the same thing for the cosine of at, then go ahead. And what you'll get is that the Laplace, it's a good exercise, so if you want to pause the video now and try it, I'll leave you to your devices. Alright, so I assume you've either tried it or don't really want to try it. So if you do the exact same thing with cosine, you get the Laplace transform of the cosine of at, which is also, if you need a hint, here you go, before I tell you the answer, Laplace transform of e to the iat plus e to the negative iat divided by 2. Alright, all hints out. This equals s divided by s squared plus a squared. Just marginally interesting. We have the exact same denominators, just swapping out the s for the a. Alright, these are the two results, and maybe I'll make a video later. Or actually, you know what? If you want to know why this is true and watch me compute it, I think I probably did it in my other video about doing this, where I did this 2 months ago. Anyway, so check that out if you really want to see the cosine of at. Otherwise, I will see you in the next video.